In combinatorial mathematics, a block design is a set together with a family of subsets whose members are chosen to satisfy some set of properties that are deemed useful for a particular application. These applications come from many areas, including experimental design, finite geometry, software testing, cryptography, and algebraic geometry. Many variations have been examined, but the most intensely studied are the balanced incomplete block designs, which historically were related to statistical issues in the design of experiments. A block design in which all the blocks have the same size is called uniform. The designs discussed in this article are all uniform. Pairwise balanced designs are examples of block designs that are not necessarily uniform. Definition of a BIBD. Given a finite set X and integers k, r, lambda 1, we define a 2 design B to be a family of k element subsets of X, called blocks, such that the number r of blocks containing X in X is not dependent on which X is chosen, and the number lambda of blocks containing given distinct points X and Y in X is also independent of the choices. Family, in the above definition, can be replaced by set, if repeated blocks are not allowed. Designs in which repeated blocks are not allowed are called simple. Here V, B, K, R, and lambda are the parameters of the design. In a table, the design is called a design or a design. The parameters are not all independent. V, K, and lambda determine B and R, and not all combinations of V, K, and lambda are possible. The two basic equations connecting these parameters are these conditions are not sufficient as, for example, a design does not exist. The order of a 2 design is defined to be n equals r minus lambda. The complement of a 2 design is obtained by replacing each block with its complement in the point set X. It is also a 2 design and has parameters V equals V, B equals B, R equals B minus R, K equals V minus K, lambda equals lambda plus B minus 2R. A 2 design and its complement have the same order. A fundamental theorem, Fisher's inequality, named after the statistician Ronald Fisher, is that BV in any 2 design symmetric BIBDs. The case of equality in Fisher's inequality, that is, a 2 design with an equal number of points and blocks, is called a symmetric design. Symmetric designs have the smallest number of blocks amongst all the 2 designs with the same number of points. In a symmetric design, R equals K holds as well as B equals V, and, while it is generally not true in arbitrary 2 designs, in a symmetric design every 2 distinct blocks meet in lambda points. A theorem of Riser provides the converse. If X is a V-element set, and B is a V-element set of K-element subsets, such that any 2 distinct blocks have exactly lambda points in common, then is a symmetric block design. The parameters of a symmetric design satisfy this imposes strong restrictions on V, so the number of points is far from arbitrary. The Bruch-Riser-Chowler theorem gives necessary, but not sufficient, conditions for the existence of a symmetric design in terms of these parameters. The following are important examples of symmetric 2 designs. Projective planes. Finite projective planes are symmetric 2 designs with lambda equals 1 and order n greater than 1. For these designs the symmetric design equation becomes, since k equals r, we can write the order of a projective plane as n equals k minus 1, and from the displayed equation above, we obtain V equals n plus 1 equals n2 plus n plus 1 points in a projective plane of order n. As a projective plane is a symmetric design, we have B equals V, meaning that B equals n2 plus n plus 1 also. The number B is the number of lines of the projective plane. There can be no repeated lines since lambda equals 1. So a projective plane is a simple 2 design in which the number of lines and the number of points are always the same. For a projective plane, k is the number of points on each line and it is equal to n plus 1. Similarly, r equals n plus 1 is the number of lines with which a given point is incident. For n equals 2 we get a projective plane of order 2, also called the Finite plane, with v equals 4 plus 2 plus 1 equals 7 points and 7 lines. In the Finite plane, each line has n plus 1 equals 3 points and each point belongs to n plus 1 equals 3 lines. Projective planes are known to exist for all orders which are prime numbers or powers of primes. They form the only known infinite family of symmetric block designs. Biplanes. A biplane or biplane geometry is a symmetric 2 design with lambda equals 2, that is, every set of 2 points is contained in 2 blocks, while any 2 lines intersect in 2 points. They are similar to finite projective planes, except that rather than 2 points determining 1 line, 2 points determine 2 lines. A biplane of order n is one whose blocks have k equals n plus 2 points. It has v equals 1 plus 2 points. The 18 known examples are listed below. The order 0 biplane has 2 points design. It is 2 points, with 2 blocks, each consisting of both points. Geometrically, it is the digon. The order 1 biplane has 4 points design. It is the complete design with v equals 4 and k equals 3. Geometrically, the points are the vertices and the blocks are the faces of a tetrahedron. The order 2 biplane is the complement of the Finite plane. It has 7 points, where the lines are given as the complements of the lines in the Finite plane. The order 3 biplane has 11 points, and is also known as the Paley biplane after Raymond Paley. It is associated to the Paley digraph of order 11, which is constructed using the field with 11 elements, and is the Hadamard 2 design associated to the size 12 Hadamard matrix. See Paley construction I. Algebraically, this corresponds to the exceptional embedding of the projective special linear group PSL in PSL. See projective linear group. Action on P points for details. There are 3 biplanes of order 4. These 3 designs are also Menon designs. There are 4 biplanes of order 7. There are 5 biplanes of order 9. 2 biplanes are known of order 11. Hadamard 2 designs and Hadamard matrix of size M is an M times M matrix H whose entries are plus or minus 1 such that H equals MIM, where H is the transpose of H and M is the M times M identity matrix. An Hadamard matrix can be put into standardized form where the first row and first column entries are all plus 1. If the size M greater than 2, then M must be a multiple of 4. Given an Hadamard matrix of size 4A in standardized form, remove the first row and first column and convert every minus 1 to a 0. The resulting 0 to 1 matrix M is the incidence matrix of a symmetric 2 design called an Hadamard 2 design. This construction is reversible, and the incidence matrix of a symmetric 2 design with these parameters can be used to form an Hadamard matrix of size 4A. Resolvable 2 designs. A resolvable 2 design is a BIBD whose blocks can be partitioned into sets, each of which forms a partition of the point set of the BIBD. The set of parallel classes is called a resolution of the design. If a 2 resolvable design has C parallel classes, then BV plus C minus 1. Consequently, a symmetric design cannot have a non-trivial resolution. Archetypical resolvable 2 designs are the finite affine planes. A solution of the famous 15 schoolgirl problem is a resolution of a 2 design. Generalization. T designs. Given any positive integer t, a T design B is a class of k elements subsets of X, called blocks, such that every point X in X appears in exactly R blocks, and every T element subset T appears in exactly lambda blocks. The numbers v, b, k, r, lambda, and t are the parameters of the design. The design may be called a T design. Again, these 4 numbers determine b and r, and the 4 numbers themselves cannot be chosen arbitrarily. The equations are where lambda I is the number of blocks that contain any I element set of points. Theorem. Any T design is also an S design for any S with one ST. A consequence of this theorem is that every T design with T2 is also a 2 design. There are no known examples of non-trivial T designs with. The term block design by itself usually means a 2 design. Derived and extendable T designs let D equals B a T design and P a point of X. The derived design dP has point set X minus P, and is block set all the blocks of D which contain P with P removed. It is of design. Note that derived designs with respect to different points may not be isomorphic. A design E is called an extension of D if E has a point P such that EP is isomorphic to D. We call D extendable if it has an extension. Theorem: if a T design has an extension, then K plus 1 divides B. The only extendable projective planes designs are those of orders 2 and 4. Every Hadamard 2 design is extendable. Theorem: if D, a symmetric 2 design, is extendable, then one of the following holds. D is an Hadamard 2 design. V equals K equals lambda 2 plus 3 lambda plus 1. V equals 495, K equals 39, lambda equals 3. Note that the projective plane of order 2 is an Hadamard 2 design. The projective plane of order 4 has parameters which fall in case 2. The only other known symmetric 2 designs with parameters in case 2 are the order 9 biplanes. But none of them are extendable, and there is no known symmetric 2 design with the parameters of case 3. Inversive planes: a design with the parameters of the extension of an affine plane, i.e., a 3 design, is called a finite inversive plane, or Mobius plane, of order n. It is possible to give a geometric description of some inversive planes, indeed, of all known inversive planes. An ovoid in PG is a set of Q2 plus 1 points, no 3 collinear. It can be shown that every plane of PG meets an ovoid O in either 1 or Q plus 1 points. The plane sections of size Q plus 1 of O are the blocks of an inversive plane of order Q. Any inversive plane arising this way is called egg-like. All known inversive planes are egg-like. An example of an ovoid is the elliptic quadric, the set of zeros of the quadratic form x1 x2 plus f, where f is an irreducible quadratic form in 2 variables over Gf. F equals x2 plus xy plus y2 for example. If Q is an odd power of 2, another type of ovoid is known, the Suzuki-Tits ovoid. Theorem: let Q be a positive integer, at least 2. If Q is odd, then any ovoid is projectively equivalent to the elliptic quadric in a projective geometry PG, so Q is a prime power and there is a unique egg-like inversive plane of order Q. If Q is even, then Q is a power of 2 and any inversive plane of order Q is egg-like. Steiner systems. A Steiner system is a T design with lambda equals 1 and T2. A Steiner system with parameters T, K, N, written S, is an n-element set S together with a set of k-element subsets of S with the property that each t-element subset of S is contained in exactly one block. In the general notation for block designs, an S would be a T design. This definition is relatively modern, generalizing the classical definition of Steiner systems which in addition required that K equals T plus 1. An S was called a Steiner triple system, while an S was called a Steiner quadruple system, and so on. With the generalization of the definition, this naming system is no longer strictly adhered to. Projective planes and affine planes are examples of Steiner systems under the current definition, while only the Fano plane would have been a Steiner system under the older definition. Partially balanced designs. An n-class association scheme consists of a set X of size V together with a partition S of X times X into n plus 1 binary relations, R0, R1, Rn. A pair of elements in relation Re are said to be ith associates. Each element of X has ni ith associates. Furthermore, and is called the identity relation, defining, if R in S, then R** in S. if the number of such that n is a constant depending on I, j, k but not on the particular choice of x and y. An association scheme is commutative if for all I, j and k. Most authors assume this property. A partially balanced incomplete block design with n associate classes is a block design based on a V set X with B blocks each of size k and with each element appearing in R blocks, such that there is an association scheme with n classes defined on X where, if elements X and Y are ith associates 1in, then they are together in precisely lambda I blocks. A PBIBD determines an association scheme but the converse is false. Example: let A be the following association scheme with 3 associate classes on the set X equals 1, 2, 3, 4, 5, 6. The entry is S if elements I and J are in relation as the blocks of a PBIBD based on A are. The parameters of this PBIBD are V equals 6, B equals 8, K equals 3, R equals 4 and lambda 1 equals lambda 2 equals 2 and lambda 3 equals 1. Also, for the association scheme we have n0 equals n2 equals 1 and n1 equals n3 equals 2. Properties: the parameters of a PBIBD satisfy. A PBIBD is a BIBD, and a PBIBD in which lambda 1 equals lambda 2 is a BIBD. 2 associate class PBIBDs. PBIBDs have been studied the most since they are the simplest and most useful of the PBIBDs. They fall into 6 types based on a classification of the then-known PBIBDs by Bose and Shimamoto. Group divisible, triangular, Latin square type, cyclic, partial geometry type, miscellaneous. Applications. The mathematical subject of block designs originated in the statistical framework of design of experiments. These designs were especially useful in applications of the technique of analysis of variance. This remains a significant area for the use of block designs. While the origins of the subject are grounded in biological applications, the designs are used in many applications where systematic comparisons are being made, such as in software testing. The incidence matrix of block designs provide a natural source of interesting block codes that are used as error-correcting codes. The rows of their incidence matrices are also used as the symbols in a form of pulse position modulation.